So this is part 2 of lesson 3.6, universal law of gravitational attraction. So now we're going to talk about what happens to the force of gravity as we vary mass and distance, okay? So here we're saying that mass is directly related to gravitational force. So what that means is if I increase the mass, right, if mass increases, then my force of gravity increases. So if you're directly related, the variables have to go up, up, or down, down. They have the same trend, okay? So if you look at this graph, right, this is how we are going to represent it graphically. You have the gravitational force, which is Fg, and you have mass on the bottom, okay? If I were to take the slope of this graph, and if you recall, slope is the change in y over the change in x. So mass is my x-axis, gravitational force is my y-axis. That means I would have Fg over m. Whoa, this looks awfully familiar. If I go to page 6 on my reference table, I will see that I have a formula that's called G equals Fg over m. So we say that the slope of this graph represents my G value, which is called the acceleration due to gravity. However, if you also look on page 6, right, we know that that's its name. Little g also has another name. So if you go to the right side of the reference table and you go to the little lowercase g, you will see not only does it say acceleration due to gravity, it will also say the following. Or gravitational field strength. So that's a new word for us, and we're going to talk about that later on in this lesson. These words are the same thing. They have the same meaning. They correspond to the same value, okay? And that's really important to know that G kind of is a little flexible in terms of its how we identify it, depending on what we're talking about, right? For the whole beginning of the year, we always were like, it's acceleration due to gravity, acceleration due to gravity. And in this particular instance, we're going to get into the habit of calling it gravitational field strength. But again, the value is the same exact thing. So you wouldn't be wrong if you said it's the acceleration due to gravity, okay? So again, you can find this formula on page 6. All right. The next relationship we have to talk about is distance. We say it's inversely related to gravitational field strength, gravitational force. So if I increase the distance between the objects, my force of gravity will decrease. And so when we say it's inverse, if I increase one, the other one must decrease. So they kind of have opposite trends. They both cannot be doing the same thing. Okay, so one must go down, the other one goes up. So if you look at this graph, right, we have Fg versus R, right? That's how we denote the distance between centers. We don't have a perfectly straight line down. And there's actually a reason for that. Because if you look at the formula for the force of gravity, it's Fg equals Gm1 m2 over R squared. This relationship right here, it's not 1 over R, it's 1 over R squared. That's what we call an inverse squared relationship. So if something is squared, whether that's the top or the bottom, and here we have the denominator getting squared, that means that the denominator will grow exponentially, right? So it's going to increase. Sorry, I know my handwriting is pretty bad right now. Yeah, grow exponentially. Okay, so I had to break it up into like two pieces. And we know that because it's squared. So I go from 1 squared to 2 squared to 3 squared to 4 squared. So that not only is it just increasing by like 1, it's getting that value squared. Okay, so it is going to increase a lot more than if it was just, just the number itself, right? If it was just a regular inverse relationship. But now it's an inverse squared, so it's going to grow even faster. Okay, so please keep in mind that this shape, it looks like a parabola kind of. And you guys learned in your math classes that parabolas come from that x squared relationship, right? So x squared gives me that parabola. So here, that's why we know that shape is appropriate, because we are growing exponentially in the denominator, okay? So now we're gonna kind of use what we just learned about and apply it to kind of see what happens to the force of gravity when we have very specific things changing. All right, so if you look to the right, you see you have Fg equals G m1 m2. This is an r squared, okay? And they tell you that G is this value, right? This is your constant, Newton meters squared over kilogram squared. So this value doesn't ever change. It'll always be the same no matter what, okay? So it says, if I double m1, well, I'm going to utilize this formula right here. This is a constant. Since constants don't change, you are going to always put it as the number 1. So you're going to say Fg equals 1. They say m2 gets doubled. Well, an easy number that we normally would use would be 1, but I'm saying that m1 is now doubled, so I'm going to use the number 2. They didn't tell me about m1, so m2, so I'm going to leave it as 1. And they didn't say anything about the distance, so I'm going to leave that as 1 squared. So now we're going to end up with Fg equals 2. So that means that the Fg is 2 times as strong compared to if nothing was changed, right? If nothing was changed, it would just be Fg, right? So this is 2 times as strong now. Now we're going to talk about if I increase the distance between the objects. So I'm doubling the distance. So again, I'm going to utilize this formula. My gravitational constant is still 1. They didn't tell me anything about masses, so I'm going to leave everybody as a mass as 1. So now I'm going to make the distance 2. Okay, so now this becomes Fg equals, so the numerator is 1, the denominator is 4 because 2 squared is 4. So now Fg is 1/4 as strong. So here it decreased, right? So it increased. Increased. And here it decreased, right? Because the distance was larger. The denominator was larger than my numerator. So now the last one, we have a combination of things. I'm saying that m1 is quadrupled and the distance between the object is halved. Okay, so we have a lot going on here. Again, the gravitational constant is just 1. If I'm quadruple, that means I became a 4. They don't tell me about anything about m2, so I leave it as 1. They say my distance is halved though, so it's 1/2 squared. Okay, so let's clean this up. So my numerator becomes 4. 1/2 squared, right? You apply your power rule for those of you in Algebra 2. So you end up with 1/4. So I have 4 divided by 1/4. When you are dividing a fraction, you do this thing called keep, change, flip. You also have use of a calculator. So honestly, if you don't feel comfortable, put this in parentheses and do it in calculator. 4 divided by parentheses, 1/4, close parenthesis, and you'll get the same answer that I'm about to get. So if we do keep, change, flip, I'm going to keep this 4. I'm going to change this division bar into a multiplication sign, and I'm going to flip this fraction, meaning that I am going to put it in its reciprocal form. So that's 4/1, and I multiply across, and I get 16. What this tells me is that Fg is 16 times as strong. Okay, again, you could do this right in your calculator. You don't have to do like this mental math with fractions. I don't expect you to. Okay, so the bottom one, it increased in magnitude compared to the original. Okay, so again, big G stays the same. You just got to follow the rules of what they're asking you to do. Pay attention. Everybody essentially starts at 1. If I triple it, it's going to become 3. If it's quadruple, it's 4. If it's a quarter of something, it's 1/4. If it's a third, it's 1/3. You just follow the rules, and they're going to tell you what quantity gets changed and how much it gets changed by. All right, so the next thing we call gravitational fields. So all objects with mass will produce gravitational fields. Well, guess what? Every single object here has mass, okay? That means every object is going to have gravitational fields, all right? So these field lines always point inwards, okay? They're going to go into the object. So if you think of your arms, like think of it as you're going to point into your head, right? They go inwards. from all directions, okay? So they can be coming from anywhere, but they're going to point into the object. The biggest rule here, and this is typically what people are going to get wrong, is field lines never, ever, ever touch. They don't ever touch each other, and they don't ever cross each other. And if you ever draw a picture where they touch or they cross, it's automatically wrong. So you really got to follow this rule. So don't make your pictures very small. Make them big, and make sure that when you're drawing the lines, you don't draw a billion lines, because the lines will end up being on top of each other, and then you'll end up getting points taken off. So if they say draw 5 lines, draw 5 lines, but make sure they're not on top of each other, so you don't run the risk of them touching and you don't run the risk of them crossing. Okay, so also with gravitational fields, right? So we have this idea of weightlessness, right? If you hear like the astronauts and they're like, yeah, like there's no gravity up here. That's not true, okay? Weightlessness is just a sensation, okay? So it's a sensation that's caused when you don't feel the effects of gravity. However, gravity exists everywhere in the universe, okay? So weightlessness, right, zero gravity, isn't real, okay? It's just a sensation because you cannot feel the effects of gravity on your body. So you're like, wow, it feels like there's no gravity here, but that is wrong. There's gravity everywhere in the universe, okay? And so think about the astronauts, they're like floating around. That's because they are far away from the Earth, so their gravitational force isn't as strong, but there's still gravity out there, okay? So field lines for a single mass will look like the following. Okay, so you kind of just want to touch the circle and then just make lines. See how none of them are touching? They're not crossing, they're not touching. We call this pattern a radial pattern, okay? Field lines between 2 masses change just a little bit, okay? So the first things first, what you're going to have to draw is like kind of a dotted line, kind of in the middle. So try to make it as perfect as possible. Mine's kind of crooked, but who cares? I'm going to label this M1 and M2 since we do have 2 masses going on. And this is what your field lines are going to look like. So we follow the regular pattern, but then something happens here where we get close to this line. So I'm going to draw a very similar pattern on this one. So if you notice, these ones right here, right, the ones that I'm highlighting, they are curved lines, right? They're not straight, they're curved. So some of you might be in calculus, you might have heard this term called an asymptote. This dotted line is kind of like an asymptote, right? So what an asymptote is where like a line gets very close to, but doesn't ever quite touch it. Okay, so if you notice, that's why these lines are curved the way they are. They're not perfectly straight. So it's like asymptotic behavior. Okay, again, it's just where a line gets very close to this dotted line, but it doesn't ever quite touch. Okay, so the lines are curving due to the presence of each other's masses. This type of pattern right here, especially this with the curves, very much kind of mimics almost like a repelling pattern that we will see later on when we talk about charges and like poles, right? So that's like an electron, or a proton, or a north and a south, okay? But they are not repelling. Keep in mind, gravity is attractive, okay? So even though it looks like a repelling behavior, that's why I put it in these like little quotation marks, it's still an attractive force though. Okay, so let's keep that in mind. So basically, some rules that we have to realize is that if the lines are closer, your gravitational field strength increases. Okay, so that just means the amount of gravity. So the tighter packed that they are means that your gravity at that location is a lot stronger. All right. And then another point that we'd like to make is that directly here in the middle, keep in mind that these forces are, these masses are exerting forces, right? So this would be like F1, and this would be F2. Keep in mind F1 equals F2. So at the center, right, of these two masses where I just drew this big dot, right, your gravitational field strength is 0. And the reason why we say that is because there is no net force there, right? They cancel out. They are equal and opposite to each other, so they cancel out. All right, and that's why we're going to say that the gravitational field strength is 0, okay? So gravitational field strength, that thing I was just talking about, well, it's the strength of a gravitational field at a particular point in space. It's just a really essential way for us to measure how much gravity there is in that location. Again, we've been using this formula right from page 6, where we'd say G equals Fg over m. We've known little g our entire lives as the acceleration due to gravity. We're just learning its other name, okay? And that's the gravitational field strength, right? When we talk about acceleration due to gravity, you will most likely use meters per second squared. Well, I told you the alternative units for little g was newtons per kilogram, and we'll see why here. You have a gravitational force, which all forces have the unit newtons, and mass for any object is going to have the units kilogram. Newton per kilogram, and that's how you get the justified units for this gravitational field strength or acceleration due to gravity. Okay, so if you think about, just the name in itself, gravitational field strength. Oh, that's how strong the gravitational field is. Like the name goes hand in hand with its meaning, right? So again, we've seen it on page 6. And back in the day, we used to use Fg equals mg to find an object's weight or its force of gravity, right, on Earth. So now we're going to use it a little differently. And we're going to use it in terms of this gravitational force in the universe. Okay, so let's do an example together. It says a person weighing 785 newtons on the surface of Earth would weigh 298 newtons on the surface of Mars. What is the magnitude, again, that's just a number, of the gravitational field strength on Mars? Okay, so that's what they want me to find. Gravitational field strength for Mars. So if I label my givens, I know that the force of gravity of Earth, which I'm going to just denote as E, is 785 newtons. I know that FGM for Mars is 298 newtons. I know that G on Earth is 9.81. You can write meters per second squared or newtons per kilogram, whatever you want to do. So just because I'm in the habit, I like meters per second squared better, I'm going to continue to write that. My unknown is GM. I don't know what that is. And my equation is G equals Fg over m. But I've come in a roadblock. I don't have m here. They never spoke about mass once. However, I do know that, and this, hopefully you remember this, mass never, ever changes, okay? Mass does not change, okay? That is the one quantity that will always stay the same wherever you are, no matter what's going on, okay? I know since mass does not change, mass on Earth, right? So mass on Earth definitely better equal the mass on Mars, okay? So with that being said, I can utilize Earth information with this formula right here to find the mass, and then I'll take the mass and plug it into the formula using the Mars information. So 9.81 meters per second squared equals 785 newtons divided by m, okay? Make it two ratios equal to each other. You're going to do your cross multiplication. 9.81 m equals 785. Divide 9.81 to isolate m. And m is equal to, 80 kilograms. Okay? So now I'm going to take that, I'm going to plug it in right here. And now I can utilize my Mars information. Right? So I'm going to utilize this. M I have, great. Fg on Mars, perfect, right there. So Gm equals 298 newtons divided by 80 kilograms. The gravitational field strength on Mars is equal to 3.73 meters per second squared, or, because this is another way you can write it, 3.73 newtons per kilogram. Both would be acceptable, okay? So Yeah, that's pretty much it. Just calculating the force of gravity and calculating gravitational field strength. Those are the only two equations you'll be asked to utilize throughout this topic.